Welcome back, everyone. So today we're going to be in the second part of our Trig Identities notes here. And so we've got more Trig Identities being the title. And really what our focus is going to be to determine a few things. But the most important among them are going to be what we call the angle, sum, and difference identities. These are going to be the ones that are most important. And then from those, we're going to be able to derive a couple of different ones, which involve double angles and half angles. So double angle and half angle identities are going to be kind of what we derive once we get there. But to start with, we're going to have to figure out what the angle, sum, and difference identities are. So in other words, if I had sine of x plus y, so sine of a sum of two expressions, is that going to equal something in general? And the same would be true maybe of cosine. And it's going to turn out that there are set expressions for these sums that are going to allow us to take something that, when combined, is not something we can work with using the unit circle, into something that we can work with using the unit circle. So to derive our identities, we're going to look at this rectangle. So we've got a rectangle drawn here, and we don't know the side lengths of the rectangle. That's going to be kind of our goal, is to figure out what the side lengths are. But we do have a couple of pieces of information. The first is the hypotenuse of this triangle inscribed inside is equal to 1. And then we've got two angles, beta and alpha. And so we're going to want to rewrite everything in terms of beta and alpha. So let's kind of look around and see what we can find here. So what we'll start with is maybe labeling these. So we could call each one of these sides something. So maybe we'll call this one C, D, E, F, G, H, I, and J. All right, so we've got a whole bunch of unknown side lengths. What we're going to want to do is figure out what each one of these side lengths are. Now what we should also do is maybe fill in some angle measures. So let's go ahead and do that as well. So what we'll notice down here is we've got 90 in alpha. So this expression here can be written as 90 minus alpha, because we know that those two angles have to add to 90. So alpha and whatever 90 minus alpha is has to add to 90 by the Triangle Sum Theorem. And then we're going to kind of do the same thing going through here, figuring out all these different expressions. So we'll notice here we've got a straight angle. So we've got this straight angle going through, so we know that's 180 degrees. So we've got 90 plus 90 minus alpha. So this angle, well, this angle has to be alpha. So that's going to be alpha, which means this is also 90 minus alpha, similarly. And then inside this triangle, in the middle, that's inscribed, we're going to get 90 minus beta, beta and 90. Get rid of that circle there. All right, so then this angle here is going to be alpha plus beta, because we know that that straight angle has to equal 180. So then this is going to be 90 minus alpha plus beta. So this is good. We're kind of filling in some angle measures here in terms of alpha and beta. So what we want to do next is figure out C and D, because those are inscribed in a triangle with hypotenuse 1. So really this triangle is on the unit circle. So if I take sine of B, or sine of beta, well, it's D over 1. So that means D is sine of beta. So we're going to rewrite that. Because now this vertical side length of the triangle is in terms of beta. We can do the same thing for C. That's going to be cosine of beta. And now we're going to want to, again, use these right triangle relationships to derive some sides. So let's go ahead and start down with this triangle on the bottom. So we'll do the same thing. We know that sine of alpha is going to equal g over cosine of beta. And we know that cosine of alpha is going to equal h over cosine of beta. So that means that g is equal to sine alpha times cosine beta. And h is equal to cosine alpha cosine beta. Okay, so we've got those two values filled in, which is good. So we'll get rid of those and rewrite them. So g is sine alpha cosine beta, and then we've got cosine alpha cosine beta. Okay, so maybe we'll look at this triangle here on the right. And we can do, again, the same thing. So sine of alpha is going to equal, in this case, j over sine of beta, which means that j is sine alpha sine beta. And then cosine alpha is equal to f over sine of beta, which means f is equal to cosine alpha sine beta. All right, so we've got these two side lengths now, which is good. So we've got sine alpha sine beta, and then we've got cosine alpha sine beta. So we'll jump over to this final portion of our rectangle and look at this big triangle with side length 1. So we'll note that sine of alpha plus beta, so we're going to use this top angle measure, because 90 minus alpha plus beta is a little bit messy. So sine of alpha plus beta is going to be e. And then cosine of alpha plus beta is going to be I. So this is cosine alpha plus beta. And then this is going to be sine of alpha plus beta. Okay. So if we look here, we've got all of our side lengths. So now what we're going to do is we're going to use the fact that we know this side length and this side length are really the same lengths. So the two vertical sides are going to be the same length, and the two horizontal sides are going to be the same length. So we'll go ahead and maybe write that down here. So we'll get rid of our previous work here. So the two vertical side lengths, so on the left I'm going to have sine alpha plus beta. And on the right, I've got two expressions. But what we'll notice about those two expressions is they have a combination of sine and cosine. So we can write this in kind of a variety of ways, but the way that I'm going to write it is, I'm going to take that bottom side length and then the above side length. So we have sine alpha cosine beta plus cosine alpha sine beta. And so this is our angle sum identity for sine. And it's sometimes called sandwich, because we can put the sines on the outside, cosines in the middle, so they're sandwiched between. And the key idea is that we're alternating between them. So alpha and beta, beta and alpha. And then doing the same thing with our horizontal side lengths, what we'll notice now is that they are combined sines, combined cosines. Now we don't have any mixing. So our top side length is going to be cosine alpha plus beta plus sine alpha sine beta for the top horizontal. And then on the bottom, that's going to be equal to cosine alpha cosine beta, which means that cosine of alpha plus beta, if we subtract sine alpha sine beta over, is cosine alpha cosine beta minus sine alpha sine beta. And this is going to be our angle sum identity for cosine. So we'll note some differences. So sine is mixed sines and cosines, whereas cosines is combined cosines and combined sines. So a way that sometimes this is remembered is as cosines stick together. So cosines stick together, and the sine which contains the sine sum identity. So not the best mnemonics in the world, but ones that will work. And some key differences also is the signs are the same for the sine identity. So if I have alpha plus beta, I'm going to have plus for the operation between the two terms, whereas cosines are the opposite. So cosines are going to be subtraction if it's addition inside of the sum. So these are going to be our two groupings of identities. And note, we've only proved it here for the sum, but you can do a similar proof for the difference. But there are myriad different YouTube videos you could watch on those. So I highly recommend looking at some proofs of these as well, some alternative proofs using geometry or using the coordinate plane. But hopefully this is just kind of a nice simple proof that illustrates the angle sum identities. So now we're going to formalize these. We're going to write them a little bit more fancy because we're going to be using these all the time. So for our sum and difference identities, again, we'll do plus minus here for both the sum and difference. So sine of alpha plus beta is going to be sine of alpha cosine beta, and then cosine alpha sine of beta. So that first angle is always going to be the first angle that we use. And the signs are the same. So if it's plus, it's plus. If it's minus, it's minus. Whereas for cosine, so we're going to have cosine times cosine and sine times sine. These are going to be opposites. So it's going to be minus plus instead of plus minus. So again, you can think of these as corresponding to each other. So these are going to be our two main identities that we use to derive everything going forward. So note, these are the ones to commit to memory. These are the ones to really know. Okay. And we'll do some examples of these a little bit later on, but we've got one more proof to go through, which is what does it look like if we have tangent of alpha plus or minus beta. So we'll do tangent of alpha plus beta to start. So we need to prove this using our identity proof kind of approach. So we're actually going to pick the left-hand side here. So we're going to start with tangent of alpha plus beta. And we're going to rewrite this with sines and cosines. So we're going to use those identities we just derived. And we'll also note that we're going to benefit from knowing what the expression should look like that we derive. So that's going to be really helpful as well. All right, so let's write out our expanded sum formulas for both of these. So we'll have sine alpha cosine beta plus cosine alpha sine beta over cosine alpha cosine beta minus sine alpha sine beta. And then from here, it's going to be a little bit tricky, but what we'll notice is in the proof here, we've got a 1. So we know that this term needs to become 1, which means we're going to divide by cosine alpha cosine beta. So we'll have sine alpha cosine beta cosine alpha sine beta sine alpha cosine beta and sine alpha sine beta. So we'll write all those expressions again, and we're going to again divide by this convenient expression cosine alpha cosine beta. And if we look, well, we're going to end up with some nice things. So our cosine betas will cancel from the first, cosine alphas will cancel from the second term in the numerator. We'll get double cancellation here, so that's going to give us the 1. And then here we get no cancellation. So we're going to end up with sine alpha over cosine alpha plus sine beta over cosine beta over 1 minus sine alpha sine beta over cosine alpha cosine beta, which are obviously going to give us lots of tangent expressions. So we'll get tangent alpha plus tangent beta over 1 minus the product of tangent alpha tangent beta. So that's our quick proof for the identity here. So again, very useful one that's going to pop up, and a little bit more complicated of an expression, but you've got a sum over a difference, and then you've got a product subtracting from 1 here. So a little bit less important than the sine or cosine sum identities, but still going to be very useful. So then it can be shown similarly that if we change it to minus beta, the only thing that changes are the signs of the numerator and denominator terms that we're adding or subtracting. So it becomes a difference in the numerator and a sum in the denominator. So this one would be essentially the same proof, but it might be one to do on your own, just to convince yourself as well. So really here we've got the main identities, sine and cosine, and then adding on to that tangent of alpha plus beta. Oops. Maybe we'll write them all together here. So these are really the 3 sum and difference identities from which all other identities are really going to derive that we use that aren't the Pythagorean identity. So again, crucial identities to know. All right, so we'll take a break here, and then when we come back, we'll start actually using these identities, getting some double angle and half angle identities as well. So if you have any questions, shoot me an email. Otherwise, until I see you next time.